So yesterday I sort of have been introducing how to write a function notation. Okay, so we started this chapter with first what is a function, and then how to write function notation. Today we're going to do a little bit more practice with actually working with that function notation. Okay, so this is what we started with yesterday. I mean, we're used to writing equations like here's a linear equation, y equals mx plus b. It's grade 9. Here's a quadratic equation for grade 10, y equals ax squared plus bx plus c, right, in standard form. And then we have a new way of writing things. These are actually linear and quadratic, are both functions. And we can express functions using function notation. For example, f at x, right? Or you can say f of x, right? Basically it means a function at x, but since x is a variable, it would represent the entire function. What we're going to do today is we're going to be a little bit more specific. What would, for example, this linear function be equal to at the coordinate x equals minus 2? And we've done these before. We've done table of values before, right? Where we would write, here's our x value, here's our y value, and then our coordinate pair, x, y. All we're doing is replacing y with f at x. Okay, and just a reminder that this is not f times x. Right? It just says this is a function of x. Right? Because you'll notice in our expression over here, this expression uses the variable x. So that's what the function is of. That's why we say f of x. Okay, and if we wanted to analyze where that function is at x equals 2, we write f at minus 2. Right? And that's information you wouldn't get by writing simply y. Right? I mean, y is in the letter y, not the question y. Right? And then we substitute 2, and then minus 2 in for x, minus 1. That's negative 4, minus 1 is negative 5. Right? So writing function notation does allow us to be a little bit more specific. So here we're saying there is some function, and at negative 2, that function has a value of negative 5. So our coordinate pair is minus 2 for x and minus y for the value of that function at x. Okay? And we can keep doing it. So at negative 1, f at negative 1, right? If you substitute negative 1 in for x, you get 2 times negative 1, which is negative 2, minus 1, negative 3. So our coordinate pair is minus 1, minus 3. Okay? And we can keep doing this for every point, just like a regular table of values that we've done many times before. But this time we're just using function notation to do it. F at 2, sorry. Okay, and then we have our coordinates, so 0 and minus 1, 1 and 1, and 2 and 3. Then you can graph them all, minus 2 and negative 5, and I'm sure we're all familiar with graphing. And it's kind of hard to see there, like that. And then connect them. This you probably could tell was a linear equation, based on the fact that it's degree 1, meaning the highest exponent for our x variable is 1. Okay, so let me just pause there. All right, so let's do some more examples. This one says, find f of 2 if f at x is x squared minus 2x plus 1. Okay, so we're just substituting, instead of x, we're substituting 2. So f at 2 is going to equal 2 squared, and if it helps, always put brackets, minus 2 times x, which is substituting 2, plus 1. And so 2 squared is 4, minus 2 times 2 is minus 4, plus 1. Those cancel, and we're just left with 1. So that means f of 2 has a value of 1. Or a coordinate pair, which we write x and f of x, is 2, 1. Okay? Now the next example gets a little bit more trickier. Okay, first, we're going to do 2 times the function g at -1, where our function g at x is 4x minus 5. So in this case, let's not worry about the 2 just yet. Let's just leave it out there, and we're just going to throw in some brackets. Now we're just going to substitute -1 in for x into our function g of x. So it's 4x, but we'll write -1, and then subtract 5. Okay, well that's -4. And -4 minus 5 is -9. Notice we're still leaving that 2 out there. We're going to deal with that last. Okay, so now we can do 2 times -9, which is -18. Let me just quickly pause. All right, so the last example can be a little bit tricky to understand because it's not saying to substitute a value. It's saying to substitute another variable with another value. So it's saying take x and replace it with a plus 2. That seems kind of like, why are we doing that? It just seems kind of like out there a bit. But usually when there's applications, right, a lot of the times in science or economics, other applications, you might want to ask yourself, okay, well, what if we replace this value with a different value with an extra amount attached to it? Right? Maybe you want to change dollars to euros, right? But you're going to add an exchange fee, right? So there are applications, but right now I'm just bringing up random examples just to help us sort of get used to function notation. So in this case, here we have g at a plus 2 is going to equal, here's g of x, but we're just going to replace x with a plus 2. So here we have a 4, and instead of writing x, I'm going to write a plus 2. And then I have this minus 5 here. Okay. Now all we need to do is expand and simplify. So we're going to use our distributive property. This will give us 4a. 4 times 2 will give us 8. And then we have to subtract 5. Here we're going to collect like terms, in which case our constants at the end are like terms. So we have 4a and then 8 minus 5, so plus 3. So that is the value of this function at a plus 2. Okay, I'm going to stop there.